Hello, everyone, and welcome to this Telit Cinterion webinar, Critical Infrastructure, Why IoT Firmware Security Matters. I'm Amanda Flink, the head of global events here at Telit, and I will be moderating today's event. Let's quickly get to know our speaker. To explain this topic today, I'm pleased to be joined by Neil Bosworth, the head of vertical segments for IoT products at Telit Cinterion. Thanks for joining me, Neil.
It's a pleasure to be here, Amanda. Thank you.
Yeah, now just before I hand it over to Neil to start our presentation, I have a few quick reminders. I'd like to remind our audience that we do have time to answer some questions at the end of the presentation. We will take a few, so simply submit a question by posting in the questions box located near the bottom of your screen. Also, please be sure to check out the resources section for some additional information. There you can find today's slide deck and a few other resources. And finally, we will send out the replay link to all attendees at the conclusion of the webinar. So with that, Neil, I will hand it over to you to start our presentation.
Thank you, Amanda. And just to say again, I'm Neil Bosworth and I work in vertical marketing at Telit Cinterion. And I've been involved in cellular connectivity for many, many years. And I'm fascinated by the evolution of IoT. We now rely on IoT for most of our basic and fundamental needs, but I wanted to do this presentation, this webinar, to highlight some security considerations for critical IoT projects. It's not a deep technical security presentation, it's more of an explanation of why IoT module firmware security really matters. And let's start with a backdrop. So, most of us are familiar with the term smart meters, which is likely because governments around the world are launching massive rollouts to help optimize energy systems. And smart meters are interesting because everyone can relate to them. Be it electricity, gas, or water, smart meters provide near real-time consumption insights, which eliminates the need for estimated bills whilst allowing more conscious use of resources. And with a bit of thought, we're all equipped with the tools to address usage patterns to save money and contribute to saving the environment. But it's more than this. Smart meters are providing data, not just consumption data, but critical data on the quality of supply at each endpoint. And so with various green agendas, the reliance on fossil fuels, and the realization that the power grids might not be able to accommodate today's power needs, a smart grid's essential to maximize efficiencies, reduce dependence on dirty fuels, and integrate distributed clean energy resources. And it's a similar story for all the utilities, be it metering or monitoring or logging. Connected sensors are deployed all over the grid to help balance supply and demand and ensure these critical mechanisms function efficiently. And to deliver this stream of information, all the assets and their sensors need reliable and secure communication. With smart grids, connectivity becomes almost as important as the asset that it's monitoring. It's invaluable. Without this complex network of interconnected sensors providing the insights to perform load balancing, we would suffer severe blackouts as the grid will become unbalanced. Now, the wind doesn't always blow and the sun doesn't always shine, unfortunately, and to accommodate these distributed energy resources, the grid needs to be tuned to make the most efficient use of clean energy. The grid needs to know when large energy consumers are operating to distribute the available power appropriately. Imagine when 4 electric vehicles roll up at the same time to charge with fast DC chargers. That's over a megawatt of instantaneous demand. And with something called demand-side management, utilities can encourage and incentivize consumers to reduce consumption at peak times, introducing voluntary schemes, allowing utilities to remotely control the consumption of certain appliances. And this network of interconnected industrial assets is critical infrastructure, and its cellular connectivity enabling or helping to enable this clean energy transition, forming the critical links either directly from the sensors in the assets themselves or as a high data rate backhaul to the wider sensor network. And buried within all of these industrial things and apparatus, the cellular module provides the key building block of the essential communication network that keeps it all running smoothly. Now, smart grid is just one example of critical industry where cellular connectivity and cellular modules form this key building block to make things smart. It's not just restricted to the utility sector. There's healthcare, there's transport, there's manufacturing, there's security, intrusion, and let's say agriculture. They're further examples of industries dependent on critical IoT connectivity through cellular networks. And let's not forget EV charging. And EV charging is essential to linking smart grid requirements with our transport needs. But of course, you can't ignore the fact that security concerns in technology are increasing. Attempted hacks to operational technology on the increase, and IoT systems are increasingly in the spotlight. In the wrong hands, especially with a backdrop of geopolitical instability, this critical infrastructure could be vulnerable. Governments are recognizing the threat to critical infrastructure, introducing new bills and proposals to address IoT devices down to the individual component level, assessing the supply chain and introducing mechanisms to monitor and address vulnerabilities. So as a first attempt to force security measures into law, the EU have activated articles in the Radio Equipment Directive, for example. So at the time of presenting, this date keeps moving, of course, but in August 2024, the new Radio Equipment Directive Delegated Act will be imposed for products marketed in the EU to address the security of networks, personal and location data, and fraud, i.e. fraud being the transfer of money. So products will need to mitigate the effects of ongoing denial of service attacks, protect attack services, implement appropriate access control mechanisms, ensure products don't contain publicly known vulnerabilities, and provide, and this is important, secure mechanisms for updating firmware and software. And once they've done this, they can achieve the CE marking, therefore being deemed acceptable to enter the European market, and projects must comply. But the thing with RED is, or Radio Equipment Directive, it only covers radio devices. So the Cyber Resilience Act, which was proposed just last year in September 22, this takes it further with requirements specifically directed towards IoT and classifies digital elements depending on their functionality and intended use. And there's a focus on the software bill of materials and correctly documenting and reporting any vulnerabilities with the chain. Fundamentally, device makers must disseminate security patches free of charge and provide a digestible explanation of what the patch is for. And in Europe and in the US, there's government programs that identify entities deemed as important or essential, and these include energy, health, transport, and water. And these industrial IoT applications would be subject to more scrutiny as a process or mechanism to identify critical infrastructure. So in all cases, not just EV charging equipment, device makers will be made responsible for the overall security of their project and really subject to severe penalties if they don't comply. So I mentioned earlier that cellular modules are forming the critical communications links. So let's take a deeper look into these cellular modules, and I like to say the unsung hero of connected critical infrastructure. The cellular module forms the exit and entry points for all the data connecting sensors and industrial things to the cellular network for internet access. Now, although this device looks, somewhat inconspicuous, just like another chip on a PCB, it's in fact quite a complicated subsystem running its own operating system and maybe millions of lines of code. It can be akin to a little industrial smartphone embedded within industrial devices, and these industrial devices that help make a country's critical systems tick. And at its core is a baseband chipset, and this is a microprocessor that runs the necessary protocol stacks to access the cellular networks and the various 3GPP technology standards required by the mobile network operators. And these chips, they're supplied by well-known semiconductor companies. But because the core functionality is difficult to integrate directly into a device, such as a smart meter or a water pump or something, equipment manufacturers normally choose to buy a module that takes care of the complexities of the core chipset. Now, from a hardware perspective, modules contain all the other peripheral components required to make the core chipset usable, which includes power and radio components, filtering, etc. It kind of makes sense for a module manufacturer to do this expert task once, source all the components en masse, and sell it as a package solution along with all the relevant approvals, such as in the US, government-based FCC or CE marking, or maybe a specific network operator approval. Now, since the introduction of 4G or LTE, long-term evolution, the cellular landscape became more complex with perhaps, I would guess, maybe over 50 frequency bands to cover the world. Now, this proved to be a major pain point in comparison to the previous 2G and 3G technologies, where global connectivity was relatively straightforward. The module manufacturer there, we kind of need to have full visibility of the cellular landscape and offer devices that support optimal frequency band groupings to make efficient devices. But when it comes to the module firmware, you really do need to have complete trust in your module supplier, because running inside a module, there's always a lot of code, and this is written by the module manufacturer. It's their responsibility to make this critical component both easy to use for both hardware developers and software developers, whilst providing additional features to ensure reliability and security. And it's worth digging just a little bit deeper here. This application AT interface provides the IoT developer the only view of what the module's actually doing. Yeah, it's used to input configuration settings, set up communication channels, as well as providing messages back to the host of any processes or issues running inside the module. And it's normally used as the data channel too, especially for typical low-speed IoT applications. Now, importantly, as this AT interface is written by the module manufacturer, it's totally within their control what's actually visible. Now, being a subsystem, the module also needs to employ its own security controls, and we'll explore this a little bit more later. In addition to the pre-written functions such as firmware update management, common internet communication protocols, and device management, the module has some capacity to run user applications, thereby onboarding some or all of the work required by the IoT application. So you can see the module is indeed a subsystem with intelligence, running applications and providing services to the IoT device. And in general, the module is used in one of three use cases. The most simplistic of which is often termed a bit pipe. It's not very flattering, but that's what it's called. So in this case, the AT command forms the complete module control along with the channel for data entry and exit. Simply put, the IoT designer uses the module as a transparent data connection to the cellular network. With a few configuration AT commands, the module simply acts as a bit pipe, transferring the thing data via the cellular networks to the internet cloud. So all the internet protocols and security handling is managed by the application processor, and the designer needs to take care of the cybersecurity complexity. That's not to say that in terms of security, all the responsibility is in the hands of the application developer. The cellular module still has a role to play in the overall security of the application. The module does, however, include some package services to ease development. Internet services provided with the module can offload all of the communications functionality from the host processor, allowing the host application processor to concentrate on running the needs of the things, be it a smart meter, an EV charger, some medical apparatus. In fact, anything can be an IoT device. So common communication protocols include the standard TCP/IP and UDP, and specific constrained device protocols such as CoAP. And being a cellular device, it can still handle SMSs, text-based SMSs, or USSD-based messaging. With the module being used as a communications processor, it takes more of the responsibility to handle the secure procedures required to connect back-end or cloud services. Which takes me to the final use case, which is the sensor-to-cloud processor. So just like a smartphone, virtually all modules have spare computing capacity. And this resource, this spare resource, can be utilized by developers to embed a complete application within the module as a strategy to reduce the overall bill of materials cost. So the developer is free to write their own applications, or just like a smartphone, take advantage of pre-written common requirements from the module manufacturer's app zone, just like the App Store, or using a dedicated and specific software development kit, and this saves time and effort. Now, aside from the main AT command interface, modules are equipped with additional ports designed to interface directly with sensors and other analog or digital peripherals, so you can put the entire system on board the module. Now, using this model, the module must take full responsibility of the application security, handling certificates or the secure credentials, data confidentiality, integrity, and authentication. And at this point, it's worth to mention device management. Regardless of the use case, the module contains functionality to inspect, modify functionality, and update firmware. Now, this is common for most connected devices, and being a self-contained subsystem, the module is no different. To use the smartphone analogy once again, the module must be updatable. It's fair to expect the unexpected, and that goes for mobile networks too. It's the responsibility of the module manufacturer to ensure that the module can be adaptable in order to evolve with network updates and tweaks, or provide a means to address security updates. And this means having the ability to perform firmware updates over the air in order to address any nuances that may occur. So module providers offer device management functionality in order to report and tweak module behavior during the long expected lifetime of industrial equipment, and provide a means for mass firmware over-the-air campaigns. Now, a few moments ago, I mentioned new regulations. It's the responsibility of the end device manufacturer to keep a device secure, and the role of the module manufacturer to provide firmware updates as necessary. And one option for the developer is to use the device management features of the module to perform mass firmware update campaigns. Alternatively, this AT port comes into play again. A service provider can perform firmware updates from its own backend to the module over the air, adding functionality to the host processor to apply the necessary AT commands and firmware update procedure to the module. In this case, it's up to the IoT service provider to perform and manage the update campaigns and ensure the process is being completed correctly. Just to reiterate, everything on the module and its confirmations regarding the tasks it's performing is managed through this AT command port. There's no other way of inspecting exactly what the module's doing. It's simply not feasible to somehow inspect all the data that's actually transmitted from the antenna to be 100% sure of what it's doing and who it's talking to. The module manufacturer is wholly responsible for providing this view of the module's actions. So, with all the news surrounding critical infrastructure and the reliance of secure IoT to keep it running smoothly, this cellular module is coming into the spotlight with some appropriate regulation. But it's not complete. There's no law dictating the use of a module, or indeed a rubber stamp stating that the module has somehow passed some security approval. This security of a system is normally covered by harmonized standards, and they're steered towards a particular industry. But for the module, the trust is somehow assumed. It's relied upon from the module manufacturer. Now, one of the good things that's happened in the IoT industry over the last few years is there seems to be a common understanding of the operational technology infrastructure. And I've not spoken about how certificates and keys are generated, but supporting the device connectivity needs a few considerations, from manufacturing of the thing to the management during its serviceable life. And as a provider of modules and the bit around them that keeps them secure, module manufacturers bear quite a big responsibility in the ecosystems of critical infrastructures, or the Internet of Critical Things. Everything that makes a thing smart goes through cellular modules. And you can see with this simple reference design, there's quite a lot of questions to ask yourself when you're doing an IoT development. There's plenty of security features of modules which more or less apply to all three use cases, be it the simple bit pipe or the full application and communications processor. IoT things are often physically isolated. That is, they're vulnerable to physical attack and potential manipulation. And let's say you can consider three kinds of attack. Number one, the classic cyber attack. This is stealing, diverting, or manipulating data. Or number two, maybe forcing the module to do something that really it shouldn't do, or you weren't expecting it was going to do. And thirdly, preventing the module from communicating altogether. If a smart device doesn't communicate, it's useless. And in the case of smart grids, it's potentially catastrophic. So secure modules are equipped with security features to fight against a range of attacks. Even for the bit pipe application, the most simple use case, the module can be prone to attack. Our modules are penetration tested in a lab by industry experts to ensure they have no known exploitable flaws. And this AT command port can be exposed. It's possible to take control of the module with physical access to this port. For this reason, access to the AT port can be locked, so only authorized users can issue commands. The official firmware images are encrypted to ensure the module can't be loaded with rogue imitations. Furthermore, with secure boot, the module will reject firmware upgrades that aren't officially signed by the module manufacturer. It's the responsibility of the IoT equipment manufacturer to guard against any known vulnerabilities. The module manufacturer needs to supply lifecycle upgrades over the life of the device, and the module needs to have some means of being securely updatable over the air with secure FOTA, or firmware over the air. This applies not just to the module manufacturer's firmware image, but also to other applications in the device or applications running on board the module. Now remember, it's a radio, and all radios can be jammed, even in the most simple use case. Now, jamming detection can't prevent this, but it can log attempts to block the radio. And with cellular, there's a dependence on connectivity platforms of the mobile network operators. So if encountering connectivity issues, it's possible to switch operators using subscription management with the SIM for connectivity continuity and keep this vital connection running. And finally, the crypto part. Another aspect of IoT devices is they often incur a change of ownership. The developer, the outsourced manufacturer, the service provider, how can you fully trust the identity of the modules not being compromised during these phases? Generating unique, diversified keys or identities can be challenging, as can keeping them secret from all the parties that may come into contact with the device. As a way to tackle this, unique identities in the forms of keys or certificates are preloaded in the module's trust zone during manufacture. And this saves the developer a huge amount of time and cost in generating and securely storing these essential elements. And they can be used to enhance the security of traditional certificate-led transport layer security, and opens the possibility of using CoAP, for example, or DTLS communications via the module's onboard transport layer security cryptographic protocol suite. So in this short session, we've examined the vital role cellular modules play in the smooth running of our most critical systems. Although often overlooked, they are in fact a complex embedded computer subsystem capable of running embedded applications along with global functionality, which in the wrong hands has the capacity to cause havoc to the systems we all rely upon. In many cases, they're more complex than the thing that they're connecting, running, say, millions of lines of code written by people in an organization that must be implicitly trusted. But unlike some elements of communication infrastructure, as yet there's no regulations governing the use or choice of supply chain of such essential devices. Critical system developers need to trust the modules do only what they're intended to do and continue running securely for years. So the question is, who wrote the firmware running inside our essential things, and who should you trust for connecting critical infrastructure? And I'll just finish here by saying that governments around the world are turning to technology to answer the demands of cleaner, greener, and more sustainable use of the world's natural resources. And electronic equipment manufacturers hold a huge responsibility to address these challenges whilst keeping our nations safe and the population healthy. And I'll just finish here with a final question. If you're involved in IoT systems for critical infrastructure, under what conditions do you choose the devices that will form your communication strategy and cellular device connectivity? And at that point, I'll open over to questions. Thank you.
Thanks so much, Neil. Just before we get to the questions, audience, I am going to drop a quick poll on your screen. If you'd like to have one of our experts contact you directly, please just go ahead and respond here on the poll, and we'll be sure to have someone reach out to you. We do have time for a few questions. I know we probably won't get to them all, but I will take a couple now. Neil, the first question I have: with all this complexity, is cellular a good choice for critical communication projects?
Well, that's a really good question, and a good question to answer as well, because cellular modules are not the only kind of wireless modules. And in all cases, wireless modules they're coupled with some processing power, be it some mesh technology, Wi-Fi or LoRa. There's some firmware running within these modules that's not in the control of the equipment maker. Now, the interesting thing about cellular is the module forms the last line of defense. So there's no firewall in the control of the IoT service provider between the thing and the internet. Also, cellular modules tend to be much more complex, therefore far more involved in the application. With regards to cellular, it's with great security, global coverage, and being licensed spectrum, it has governance, along with a strong infrastructure, easy deployments, and flexibility in the required bandwidth. Cellular is very popular for crucial connectivity. There's also the option of private cellular networks, and this could add an added layer of security and control. But it's fair to say governments do have control over the cellular infrastructure. They can, or indeed have, introduced policies towards core equipment supply, and this is all regarding security concerns. Hope that answers the question.
Thanks, Neil. Next question I've got here. Why would people only use the module as what you call a bit pipe when the module is capable of lots of tasks?
Okay. This is a classic question. Sometimes developers like to take control of as much as possible within their own trusted environment, which is their application processor. This sometimes makes sense, but there are still features of the module, the supply and the support, which shouldn't really be overlooked. Some industries won't consider a module without secure boot, for example. The AT port can be open to attack. There needs to be some secure update mechanism, jamming detection, the securing the continuity of a network operator service. The module still needs to do all of this. And fundamentally, if you do this, you're basically running two computers. You're kind of attaching an external computer, being a module, to the internal computer, which is your host processor. And it's the external computer. Remember, it is a computer. It's not just a modem. It's this computer that's making a smart thing smart. Hope that answers the question.
Great, thanks. Next question I have here. I saw on your slide IMEI protection. What is this? Okay.
So when considering the module as just another component on the PCB, and a PCB often has hundreds of components on it, there's something literally unique about cellular modules. They are individually traceable. So once the IMEI number, which is the module's unique ID, once it's in, it can't and shouldn't be able to be reprogrammed. And if it could, it would cause havoc in the networks. But if this ID is used in an application, you've got to remember it's not a secret. For a start, the number's written on the package, it's written on the outside of the can. And also, module manufacturers can keep records of who they ship the module to. So this IMEI number, although it needs to be locked in, remember, it is no secret. That's it.
Great. Thanks, Neil. I believe that's all the time we have for today. Not to worry if we didn't get to your questions. We'll be sure to have somebody follow up with you directly. Audience, please be sure to check your inboxes in the coming days for that replay link. Neil, thank you so much for your time today, and thank you everybody who joined us.